Let's get started here. And so here we go. Chemistry 3101. This is chapter 4, alkanes and cycloalkanes. So that's the topic of the entire chapter, just talking about hydrocarbons. And we spoke about alkanes when we looked at functional groups. An alkane technically isn't a functional group, but if we compare these various types of hydrocarbons here, hydrocarbons are simply compounds that contain only hydrogen and carbon, no other elements. And we know that a carbon-carbon bond is completely nonpolar, and we know that a carbon-hydrogen bond is considered nonpolar. So all hydrocarbons are nonpolar. But if we break the classes of hydrocarbons down, you can see that we have saturated hydrocarbons and unsaturated hydrocarbons. So unsaturated hydrocarbons, these would be the alkenes, the alkynes, and aromatics as well. So compounds like ethylene, acetylene, and benzene. But we're going to talk most of the time about saturated hydrocarbons, right? Alkanes. They have the maximum number of hydrogens bonded per carbon atom. And we're going to talk a lot about how to name these type of compounds, how to name alkanes. Well, just a little bit of history on naming alkanes and naming organic compounds in general. It says that many organic compounds have common names. Okay, but in 1892, chemists were discovering more and more organic compounds all the time, and so they had to come up with some kind of systematic way of naming them. And so they get together, and first they came up with what were known as the Geneva rules, which later led to the IUPAC rules, which is the International Union of Pure and Applied Chemistry. If you just look at these four molecules here, you see we have formic acid. Now, where does that name come from? It doesn't come from any kind of systematic name. It's actually named after the Latin word for ant, formica. Urea is isolated from urine, so it's kind of easy to see the connection there. But then you get into some that are a little more interesting, like morphine. Like, where does that name come from? Well, it's actually named after the god of dreams, the Greek god of dreams, Morpheus. And barbituric acid is even funnier. It was named by Adolf von Baeyer, who discovered it, and he simply named it after a woman named Barbara that I guess he was, it says here, in honor of. I think he was just infatuated with her, is what I read. Anyhow, now when we're talking about the IUPAC system, this is a systematic way of naming compounds. So sometimes you'll hear me refer to it as the IUPAC. Other times you'll hear me refer to it as a systematic way of naming compounds. They both mean the exact same thing. IUPAC, again, stands for International Union of Pure and Applied Chemistry. So this is a set of rules that we can use to name compounds that will be agreed upon within the entire scientific community. And the reason that's important, especially nowadays, is that it's a big world, right? And well, I guess it's a small world in some ways. With the internet, we're able to communicate with scientists all across the world. And so if we're naming a molecule, we want to be able to communicate the name of that molecule to scientists in any other country on the planet. Okay, so we don't have time to memorize or to learn all of the rules of IUPAC nomenclature, but we're going to learn some of the basic rules in Chapter 4. So the first rule that you're going to learn is what's called identifying a parent chain. Now, a parent chain is simply the longest consecutive chain of carbons in a molecule. Here we have an alkane, saturated hydrocarbon. We have lots of carbons, lots of hydrogens. And if we were to try to find the longest carbon chain, you might start and say, well, if I start here, 1, 2, 3, 4, 5, 6, 7. Okay? But if you look a little deeper, you might say, okay, well, let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9. And in fact, you find that 9 carbons in a row is the longest chain. Now, you might be asking me, well, how do I find that, Mr. Dion? And the answer is trial and error. Okay, you just keep trying until you find the longest carbon chain. There is no better answer than that. Simply trial and error. Now, what about these carbon chains, right? If I have a chain of 9 carbons, I have to know how to name that. I have to know how to name that parent chain, and you have to memorize the names of the first 10 is what I said, or what it says in the book. I think it says to memorize the first 10 straight chain alkanes. Sometimes you'll hear these called N-alkanes. So N-alkanes, which just means they're linear, and that just means normal alkanes or straight alkanes. We'll just put here straight alkanes, because of course an alkane can have branching. but they start with 1 through to 10 carbons. So you need to memorize it. If you have only 1 carbon, it's methane. If you have 2, it's ethane. 3, it's propane. 4, it's butane. 5 is pentane. 6 is hexane. 7 is heptane. 8 is octane. 9 is nonane. 10 is decane. I think it's kind of handy to know these two here, undecane and dodecane, because they do come up from time to time in the class, 11 carbons in a row and 12 carbons in a row. But the first, the first 4, I think, are not nearly as intuitive. Methane, ethane, propane, and butane, not nearly as intuitive as these ones here, right? Pentane, you think of a pentagon, has 5 sides. A hexagon has 6 sides. Hept, in French, the word 7 is sept, which, kind of looks like it's got the EPT in it. So that's how I remember that one. And then octane, you think of an octagon. Nonane, non kind of sounds like 9. And then decane, well, the connection is obvious, a decade. Anyhow, all right. So you have to have memorized methane through to decane. And again, I would recommend memorizing undecane and dodecane as well. All right. So what if the parent chain is cyclic, right? We're going to see many organic compounds that are alkanes where the parent chain will just be a cycle of carbons. So they'll all be put in some kind of ring. Well, in that case, you look at the number of carbons and you prefix it with cyclo. So if we look at the triangle here, that's cyclopropane. Where does that come from? Well, it's got a total of 1, 2, 3 carbons in it. So we put cyclo before it because they're in a ring, right? They're in a ring. And then propane is what we would call a straight chain hydrocarbon, right? That would be propane. So this becomes cyclopropane, right? If you have 4 carbons in a row, 1, 2, 3, 4, this is called butane, the same butane that's in a butane lighter. If you put them in a ring, however, you call that cyclobutane, right? We have 1, 2, 3, 4 carbons here. If you have 5 carbons, you would call it cyclopentane, and you can probably guess that if you have 6 carbons in a ring like this would be called cyclohexane. I'm not the master at drawing 7-membered rings, but if you have a 7-membered ring, it's going to look like this. This would be cycloheptane, and if you have an octagon, that would be cyclooctane, so on and so forth. So there you go. We're not going to see a whole lot past cyclooctane in this class, however. Okay, well, how do we name substituents? Because we know that we can have a straight chain of hydrocarbons and we can have branches off of that hydrocarbon. Well, we have to come up with names for those. If you look at the one that I'm going to circle here in blue, if you look at this one here, right, what is that made of? If I draw that out, we have the bond coming off of the chain, then we have CH2, and then we have CH3, like that. Okay, that's what's inside the green box there that I have circled in blue. CH2, CH3. Well, if I had CH3, that's 2 carbons, that would be called ethane. And so what you do, if you drop the E on the end and you replace that with il, so it would become ethyl. So this is an ethyl group. The same thing applies to all the other hydrocarbons. If you remove 1 hydrogen from a methane, you get methyl. Then we go to ethyl, propyl, butyl, pentyl, hexyl, heptyl, octyl, nonyl, and decyl. So for example, if we look at this one right here that I'm circling in blue again down on the bottom, could anybody name that substituent that's down there?
Is that propyl?
Yeah, it's a propyl, exactly. Because it's got 1, 2, 3 carbons in it, right? If you have 3 carbons in a hydrocarbon, if we back up, 3 carbons in a hydrocarbon is propane. So if we remove a hydrogen and make it a substituent, it becomes a propyl. And then over here, we have a methyl, like that. So you need to be aware of these substituents. Now, if you find it a little overwhelming looking at it on a Wednesday morning, the more you practice it, the better you will become at recognizing substituents, so much so that eventually they'll just become second nature and you won't really have to think about them. Now, what about a ring? If we think about having a substituent on a ring, and this is a propyl group, we just saw this is a propyl here. A ring can either be a parent chain or it can be a substituent depending on the situation, and it's based on number of carbons. Let's look at this molecule right here. If we look at the longest chain of carbons, okay, it would be the 1, 2, 3, 4, 5, 6 carbons in this cyclohexane ring. Remember, when we're numbering carbons, we can't go 1, 2, 3, 4, 5, 6, 7, 8, 9. It doesn't work like that. We can't backtrack over a carbon. That would require you to step back over this carbon, and you can't do that. So the longest chain in this case has 6 carbons. Here I only have 3 carbons in the propyl. So since the propyl is smaller than the parent, it becomes propyl cyclohexane, right? This is just a substituent, the propyl. Another situation is where a ring can be a substituent, and that's when the parent chain, okay, the straight chain is longer. So in the parent, we have 1, 2, 3, 4 carbons. And since the cyclopropyl is on the first carbon, we call it 1-cyclopropyl butane. Okay, now one thing I didn't address was the il for the cyclos. So if you have a ring that's a substituent, okay, let's say you have this, that would be cyclobutane. If it's a substituent on a bigger chain, like let's say you have 1, 2, 3, 4, 5, 6 carbons like that. In this case, it would be cyclobutyl. So cyclobutyl, okay? So a substituent, same thing. You drop the E at the end and you replace it with il. All right, let's keep looking at substituents. I'm not going to ask a whole lot of questions about complex branches. However, you have to be aware of it. It could come up on a quiz and it could come up on the final exam. And in fact, the only example that I could find in the textbook that brings up complex branches that when I was looking this morning is question 4.13. And I'm not even sure if I assigned that one. So make sure to take a look at it. But if you have something that doesn't have a simple common name, so like a substituent that's in this green box here, what do you do to name that? To name that substituent, okay? You start by naming the longest carbon chain within the substituent, which you can see here. It's got 4 carbons, right? 1, 2, 3, 4. They're all numbered. Then you're going to name that substituent, right? Based off of that chain. Since it's 4 carbons, it's a butyl, right? You have butane and butyl, okay? And then you've got a substituent on here, don't you? Right? You have a methyl. So this would be a 2-methyl. A 2-methyl. So you have a methyl on the second carbon there. So this would become, altogether, it would become 2-methyl butyl. Now, something else I want to point out, and this is another rule that you have to be aware of. I can't remember if I have it on another slide or not. But anyhow, whenever you have numbers and letters separated in a name, you always separate them by a hyphen. Okay, the numbers and letters are always separated by a hyphen. So numbers, maybe we'll write it down. Numbers and letters, okay? You're going to separate by a hyphen. If you have numbers, come on, numbers and numbers, okay, you're going to separate those by a comma. And if you have letters and letters, you have no separation, okay? You're just going to put them together. That's why the methyl and the butyl, there's no separation there. Okay, well, what other kind of substituents can we have? You need to memorize some common substituents, and we're going to go over them in the next couple of slides, okay? These are common because they show up so often in organic chemistry. They show up all the time. Well, if we have our parent, our longest carbon chain, and it has 3 carbons coming off of this, right? We have a CH2, CH2, CH3. We already agreed that that would be called propyl. The number of carbons and hydrogens in here is C4H9, right? Inside that black circle that I've put there. If you look inside this circle over here, you'll also see that this is C4H9, but it's a different arrangement. Okay, so this alkyl group, or this substituent, is a constitutional isomer of a propyl, and we call it an isopropyl. Now, the name that's given to it, if it was named as a complex branch, is shown below. You see it says 1-methyl ethyl down here. You will virtually never have to use that. You have to have memorized propyl and isopropyl. So how does an isopropyl differ? You have a CH and you have a CH3 here and a CH3 here. Okay? All right. Some other substituents you have to memorize. You might be thinking, well, what if I have more carbons? It's going to get more complex, right? If we have a butyl, CH2, 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 CH3. Did I say C4H9? Jeepers, nobody stopped me. Anyhow, so the formula for all these, I'm thinking too far ahead, is C3H7. My mistake. There we go, C3H7. When we get to a butyl, it's C4H9, and there are several ways that you can arrange those. You can have what's called a sec-butyl, an isobutyl, and a terp-butyl. You need to have all 4 of these memorized. Okay? The way that I memorize these is that the carbon, the first carbon in the sec-butyl is a secondary, it's got 2 carbons attached to it, so I think of secondary like that. Anyhow, anything that's an iso always ends off with 2 methyl groups at the end, like this. So you have an isobutyl, the same thing with an isopropyl, right? You have 2 methyl groups kind of at the end of the branch. And then the last one is a terp-butyl. So that's where we have a carbon and it's attached to 3 methyl groups like that. Okay, so you need to have memorized, methyl, ethyl, propyl, isopropyl, butyl, sec-butyl, isobutyl, and terp-butyl. Another thing I want to mention about these common names that I don't even know if he brings this up in the textbook or not, but it's kind of like addressing an elephant in the room. If you notice that isopropyl, there's no hyphen, there's no space or anything. And the same thing with isobutyl, there's no hyphen, there's no space. But if you look at sec-butyl and terp-butyl, they both have the sec in the tert italicized, and then you have the hyphen. That's just a rule that you have to know. You have to know how to name it properly. So sec and tert, they have these hyphens in them, whereas iso doesn't. And if you're wondering, oh, jeepers, Mr. Dion, this is complicated. Well, again, the more practice that you get at it, the stronger you will become. And trust me, many students have studied this and have mastered it, and so you will be able to do that too. All right, now our book goes into groups that have, or alkyl groups that have 5 carbons. I'll just draw them down here. Now, this is something that I didn't include in my slides, but if you have an R group as your parent, let's say that's your parent, and then you have 1, 2, 3, 4, 5 carbons, this would be called a pentyl group. Now, in the book, he mentions the isopentyl and the neopentyl. So isopentyl and the neopentyl. And they don't come up a ton in this class, but it might be nice for you to have these ones memorized too. So an isopentyl, just like an isobutyl or an isopropyl, has the 2 methyl groups at the end, right? You have your isopentyl, okay? And a neopentyl looks like this, where you have a CH2, and then you have, this thing over here. Again, I didn't even include those in my slides. However, they are in the book. They will show up once in a while. Okay, not an abundance of pentyl groups do we look at, but they can show up from time to time, so you should be aware of them. All right. One other thing I want to address before we move on is when I keep saying things like CH2, CH, and CH3. Now, you've heard me say this because I said it on the last slide, that a CH3 group, okay, that's called a methyl, right? We learned that this morning. Okay, that's a substituent. Okay. Whenever we have a CH2 in a molecule, it's not called a CH2. It's actually got a name. It's called a methylene. Okay, so instead of me saying CH2, CH2, we say methylene. There's another methylene. And if you have a CH, okay, it's actually not called a CH. It's got a better name than that. It's called a methyne. So a methyl, a methylene, and a methyne. And those will come up, time and time again in this class. All right. Now, if you're having, if you're getting like a panic attack about putting all this together, what are all these things? Methyl, ethyl, propyl, isopropyl, butyl, terp-butyl, sec-butyl, isobutyl, right? Well, let's slow down for a second here, and let's get back to the parent chain and thinking about just the substituents on that parent chain, okay? So rule number 1 is when you're putting the IUPAC name together. Let's see if we can take what we've learned this morning and actually name a compound. Well, of course, you would first start by identifying the parent chain. Now you can see that the parent chain has been identified here. You got 1, 2, 3, 4, 5, 6, 7. So it's some kind of heptane. And the person did the same thing here. But you see that one way is correct and one way is incorrect. You see that there is a methyl group, right? There's a methyl group here. Now you would call this a 2-methyl because it's on the second carbon. You would call that a 2-methyl. If you started numbering over here, it would actually be called a 6-methyl. Only one of these can be correct, okay? There isn't a bunch of different ways to name a compound. Like somebody can call it Greg, another person calls it Larry. No, there's specific names for all organic compounds that are either correct or incorrect. The reason the second one is correct is because of this rule right here. When one substituent is present, you number the parent chain so that the substituent gets the lowest possible number. What's a lower number? 2 or 6? 2 is a lower number. So that means that this is the correct way to name it, and this would be incorrect. So again, we find that longest carbon chain, and we give the substituent, if we only have one, we give it the lowest possible number. You might be thinking right away, what if I have more than one substituent, Mr. Dion? What do I do then? Now, this is a rule that I find, and I've taught this class a long time. This is a rule that sometimes some students will try to make it more complicated than it is. Let me explain the rule to you. If you have more than one substituent, you find the longest carbon chain, same as always, and you number it, watch carefully, to give the first substituent the lowest possible number. Whichever substituent you can give the lowest possible number, do that, and that's the end, okay? Everything else is going to be numbered based off of that. The problem that I see students run into is that they'll overthink this rule, and they'll think that it's something about adding numbers up and getting a lower sum or something crazy like that. It's got nothing to do with that. The rule is simply give the first substituent the lowest possible number. To hell with the rest of them. Just number them what they are. If you give the first substituent the lowest possible number, you, my friend, will get the right answer. Let me show you what I mean. You see the correct way is down here on the left. So they numbered the longest carbon chain. It's got 7 carbons. The way that this is done, I have a methyl group at carbon 2. So this would be a 2-methyl. And then I have 2 methyls on carbon 5. So that would actually be called a 5,5-dimethyl. And I'll get into the prefix di in a second. Okay. But this is 2 a lower number than 5? Yes. And 2. So that means this is correct. If you had gone the other way, your first substituent would be on carbon 3. So the rule is simply the first substituent has to be on the lowest possible number of a carbon. Okay? Give me a thumbs up if that rule makes some sense to you. It's a very important rule. It's got nothing to do with tallying this up. That equals 12, and that equals 12. It's got nothing to do with adding numbers. And I've seen students try to do that. Great. Thanks, Moira. Perfect. All right. Well, let's keep going from there. And don't worry, we're going to get to some examples. But before we can try some examples, there's a bunch of rules that you have to look at, because you can run into problems if you only study like 2 rules and then you try to name compounds. I know I would run into problems doing that. Let's see here. It says if there's a tie, then you number the parent chain so that the second locant gets the lowest possible number. The locant, the word locant, is just a SATSI name in organic chemistry that we use for number. Okay, it means nothing more than number. So a 1, a 2, a 3, right? Look, here's the correct way right here. It wouldn't matter if you numbered going this way. Okay, the first substituent is at carbon 2. If you even did it the incorrect way, your first substituent is at carbon 2. You also have a substituent at carbon 3. Okay, and if you had done it this way, your second substituent would be at carbon 5. And so if there's a tie with the first 2 substituents, or with the first substituent, then you keep going until you have more and more substituents, and you give the next one the lowest possible number. So 3 beats a 5. It's lower than a 5. And so that would be the correct way. What other kind of rules can we run into? What if you have something like this? You've got a substituent on carbon 1 and you've got a substituent on carbon 5. Even if you do it this way, you've got a substituent on carbon 1 and carbon 5. Well, we've looked at methyl, ethyl, propyl, isopropyl, butyl, tert-butyl, sec-butyl. But we haven't talked about the halogens. If you have a fluorine, that's called a fluoro when it's a substituent. If you have a chlorine, that's called a chloro. Try to be consistent here. If you have a bromine, you can probably guess that's called a bromo. And if you have an iodine, that's called an iodo. Okay, so here we've got a chloro and a bromo. Well, if you get into a mess like this, all you do is assign the lowest number by the alphabet. So B comes before C in the alphabet, so bromo wins over chloro. Okay, that's that one. Same rules apply for cycloalkanes. Look, if you have either of these cycloalkanes here, what's the longest carbon chain? It's 6 carbons, right? Going 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. Both these molecules are identical. There's 3 methyl groups. If you start numbering this way and you number this carbon as carbon 1, I just circled in blue, then you have 1, 1, and 3. If you do it the incorrect way, going counterclockwise here, you'd have 1, 3, 3. Here's the tiebreaker. A 1 beats a 3. 1 is lower than 3, and that's it, my friends, okay? Nothing more than that. I never said it was simple, but that's the way it goes. Okay, so if we look at a summary, to complete the whole name, you put the number and the name of each substituent before the parent chain. You do it in alphabetical order. I want to talk about this alphabetical order for just a second, okay, or in a second, I should say. It says a prefix is used if multiple substituents are identical. Now, in terms of this, I don't know how we went from number 1 to number 5. That escalated quickly. Anyhow, so rule number 2. So you saw the prefixes. So if you have 2 of a substituent, you call it di. If you have 3 of the same substituent, it's tri. If you have 4 of them, it's tetra. And if you have 5 of the same substituent, it's penta. Past penta, I don't think we'll look at any hexa, substituted anything in this class. But I want to talk about these prefixes. Prefixes like di, tri, tetra, penta, tert, we saw that this morning. What else? Sec, we saw that this morning. Those prefixes you ignore, okay? The only prefixes that you don't ignore in organic chemistry are these 3 right here. Iso, you don't ignore that one, and cyclo and neo. So if you're wondering, what do you mean by ignore? Okay, well, let's say you have a triethyl, okay, for example, and let's say you had cyclobutyl, okay, as substituents. The triethyl, you ignore the prefix. So you alphabetize according to the letter E. If you have cyclobutyl, you don't ignore the prefix. You alphabetize it according to the letter C. If you're wondering about the sec-butyl or the tert-butyl, again, you ignore those prefixes, and so you would alphabetize according to the letter B. So if we go over all the rules, here we go. You identify the longest carbon chain. You identify and name the substituents. Methyl, ethyl, propyl, isopropyl, butyl, tert-butyl, sec-butyl, isobutyl, pentyl, neopentyl, isopentyl. You give a locant to each substituent. So a locant, again, is just a number. Then you put them in alphabetical order before the parent, and that's it. That's how you name an alkane. And we're going to look at a few examples. Now, I looked in my slides this morning, or my notes, and I noticed, okay, here we go. We have a compound here, and we want to try to name this compound. So this slide, I'm just kind of do it in a step-by-step approach here, okay? The longest carbon chain here is 6 carbons, right? The 6 carbons in this ring. So that tells you that this compound is some kind of cyclohexane, right? It's some kind of cyclohexane. So that means that the name always ends with the parent. This compound ends with cyclohexane. The rest, we're going to figure it out. When we go to number this ring, do we start here with this is a tert-butyl group, tert-butyl. This is an ethyl group, and these are both methyl groups. So we would call this a dimethyl since they're both on the same carbon. Anyhow, where are we going to start numbering? Let me get the blue pen out here. Which carbon are we going to start? Are we going to start at 1, 2, 3, 4? If we were to do that, we would have 1, 2, and 4 and 4, right? We'd have 1, 2, 4, and 4. Looks good. Starts on the number 1. Number 1's a pretty low number. But hold on a second. What if we started, and I'm going to try to erase some of this stuff, okay? What if we started here? We said 1, 2, 3, 4, 5. So then we'd have 1, 2, and 5, 5. Well, that doesn't work. 1, 2, 4, 4 beats 1, 2, 5, 5, doesn't it? Right? Because a 4 is lower than a 5. So we're still good. But there's a better option, isn't there? Right? And hopefully you noticed, based off of my notes, that the best option would be this one here. If we start where the dimethyls are, 1, 2, 3, 4. Because then we have 1, 1, 3, and 4. A 1 beats a 2. And so this is correct and this is incorrect. So the numbering that I have on the ring right now, 1, 2, 3, 4, 5, 6, that is the correct way to number that cyclohexane ring. Now we have our substituents. We have a tert-butyl in the 4 position. That means we have a 4 tert-butyl. We have an ethyl at the 3rd carbon. So that's a 3 ethyl. And we have 2 methyls on the same carbon. So instead of saying one dimethyl, we give a locant for every single substituent. A locant is a number, so it's 1,1-dimethyl. Di meaning two. So we have 1,1-dimethyl. How are we going to alphabetize these? We ignore all prefixes except iso, cyclo, and neo. And iso and cyclo and neo don't even show up in any of these substituents. Cyclo shows up in the parent, but the parent is always last. So that means the tert-butyl is going to be alphabetized by the letter B. The ethyl will be alphabetized by the letter E. And the dimethyl will be alphabetized by the letter M. So when we put all of this spinach together, I'll just erase this and we'll start over. Let's do it. Remember, we separate numbers and letters by a hyphen. We separate numbers and numbers by a comma. And we separate letters and letters by nothing. So we're going to have a 4-tert-butyl because we start with the letter B, 4-tert-butyl, like that. After that, we have our 3-ethyl. After that, we have our 1,1-dimethyl. And then we don't separate that from the parent, which is cyclohexane, like that. Again, our alphabetization was B, E, and M. We ignore the tert prefix and we ignore the di prefix. Again, the only prefixes we don't ignore in organic chemistry are iso, cyclo, and neo. All right, well, with that in mind, let's take a look at a couple of compounds and see if we can name them. Could anybody tell me in B what the longest carbon chain is? How many carbons are in the longest chain in B?
The cyclohexane?
Yeah, 6 carbons, right? There are 6 carbons in the longest continuous chain. I have 1, 2, 3, 4, 5, 6 in here, right? If you want to highlight it, 1, 2, 3, 4, 5, 6, like that. I have 6 carbons. That is my longest carbon chain. 6 carbons in a straight chain is hexane. Since these are in a ring, this must be some kind of cyclohexane. Now, based off of the groups that we looked at, the substituents, you see that this substituent has 1, 2, 3, 4 carbons. Could anybody identify this substituent based off of the substituents that we looked at this morning?
Is it butyl?
It's a kind of butyl, right? Because it has 4 carbons. If it's just plain old butyl, you would have the parent, and then you would have 1, 2, 3, 4, right? That would be a butyl. But since you have, like I told you, if you have 2 carbons coming off of the methine, like this is called a sec-butyl group. So this is a sec-butyl. Let me just delete that. So this is a sec-butyl. So that means that this compound is sec-butyl cyclohexane. Now, if you're thinking, whoa, Mr. Dion, where's your 1 and your 2 and your 3 and all that stuff? For us to put a number 1 here is redundant. It's inconsequential because since there's only one substituent on the ring, you don't have to tell anybody where it is. Okay, if there's only one substituent, of course it's going to be on the first carbon. So that's another nuance, is that you don't have to put a number here. So this is simply sec-butyl cyclohexane. Sec-butyl, I'm trying to make it all one word. Sec-butyl cyclohexane. There you go. So you've named an organic compound. Let's try another one. We'll try this one over here. I'm sure that somebody was looking and found the longest carbon chain in this one while we were talking about the first one. Could anybody tell me how many carbons are in the longest chain in F? Yeah, thanks, Byron. There's 8. Absolutely. Right? And how did you find that? By trial and error. Sometimes it just takes, you got to spend a little time looking around. Dr. Diaz, I share an office with him. He loves to give me an organic compound and go, hey, find the longest chain, give me something really complicated, and then he'll laugh at me if I make a mistake or something. So, of course, I will never laugh at a student if they make a mistake. I'm talking about gigantic organic compounds, with 100 carbons, and he'll ask me to find the chain and think it's a joke. Anyhow, a little chemistry humor there. Anyhow, the longest carbon chain, like Byron said, it's got 1, 2, 3, 4, 5, 6, 7, 8 carbons, like that. Anything else is incorrect, right? If you said, well, there's 6 carbons here, that's a pretty big number. Well, there's a bigger chain, right? And now we have a ring as a substituent. So this is actually a cyclohexyl. Anyhow, I'm getting ahead of myself because we still haven't decided how to name or how to number the carbon chain. I'm going to throw this out to my students. If we call this the left and we call this the right, would you start numbering from the rightmost carbon or the leftmost carbon, the way it's drawn?
The
The
red.
left.
So which one would I start? I would start on the right. Okay, now if you're wondering, why is that, Mr. Dion? Because we want to give the first substituent the lowest possible number. If you started over here, you'd have 1, 2, 3. Your first substituent would be on carbon 3. If you start from the right, however, you have 1, 2, and your first substituent is on carbon 2. So that's the correct way. We have 1, 2, 3, 4, 5, 6, 7, 8. So this must be some kind of octane. Now we're going to give a locant, a number, and a name to each one of the substituents. We have a 2-cyclohexyl, so we separate those by a hyphen. We have a 4-ethyl, okay, and then we have two methyl groups. We have one here and here, and so that would be a 5,6-dimethyl, okay? Now we need to alphabetize those. We ignore all prefixes except iso, cyclo, and neo. So we're going to alphabetize according to the letter C for 2-cyclohexyl, the letter E for ethyl, and M for dimethyl because we ignore that D. That's a prefix. All right, so if we put all that spinach together, I'm going to start over here. We have 2-cyclohexyl, 4-ethyl, 5, 6, dang it, I'm still going to run out of room. Dimethyl. I'll just move this out of the way here. There we go. So, and then octane, since our parent has 8 carbons. Now, you got to remember that you might look at problems like this when you're practicing and say, "Oh man, that's complicated. You know, that's a big molecule." But if you learn the rules, right? And one thing I've learned teaching chemistry is that science students love rules. They're like, just tell me the rules, I'll figure them out, and then I'll be able to answer anything if I understand the rules correctly. That's true with nomenclature. If you understand the rules well, you will be able to master nomenclature, okay? I worked with a guy who was a nomenclature expert, and it's pretty cool when somebody knows, you know, all the rules for complex molecules. Anyhow, let's see here. Naming a bicyclic compound. Wow, what the heck is this? What is this thing here, okay? We looked at bicyclic compounds quickly in chapter 2. I kind of showed you a couple of structures, and I said, well, you know, in this molecule here, you have 7 carbons, right? You have 1, 2, 3, 4, 5, 6, and then you have a 7th here in the bridge. That's one way of drawing it, or you could draw it like this. They both represent the exact same thing. But what we're interested in is naming the compound. All right, we're going to figure out how to name bicyclic compounds. You're like, what? I'm going to learn how to name that funny looking thing. Yeah, you are, okay? And it's not that complicated if you just, again, learn the rules, master them, and trust me, you'll be able to get it. So the parent, how many compounds are in the parent in both of these? The answer is 7. So you take all the carbons in the bicyclic system, you add them up. We have a total of 7 carbons, right? There's 7 carbons here, okay? So that means that the parent is going to have bicyclo in front of it, and then you're going to have heptane. So this would be some kind of bicycloheptane. But you don't just do this. You don't put bicycloheptane, okay? That doesn't tell you enough. There's nothing wrong with bicycle, and there's nothing wrong with heptane, but you don't do it that way. Let me show you. It gets a little funky. What you do is you do this. You go bicyclo, okay? Then you put an open square bracket and then a closed square bracket. Then you put heptane. And inside those square brackets, we're going to put some numbers. Some numbers? Yeah, we're going to put some numbers in there. What are the numbers? Okay, the numbers come from the carbons that are off of the bridgehead carbons. And you're like, what the hell is a bridgehead carbon, Mr. Dion? Let me show you. The carbons where the bridge is attached, right? This is a bridge here. Those carbons are called bridgehead carbons. Okay, so both of these are, it's called a bridgehead, and this is probably on another slide, but whatever. Okay, those are called bridgehead carbons. Okay, they're part of the 7 carbons, right? They're carbon, you know, I'd have the number 2 and 4 over here. Those are bridgehead carbons. Okay, same molecule. Well, the numbers that go in here are the number of carbons that are in the bridges. So this is a bridge here. Maybe I'll use a different color. I'll use green. This is a bridge here. This is a bridge here. And this is a bridge as well. How many carbons are in each of these bridges? Well, let me use a different color for this one. Maybe I'll use blue for this one here. The two bridges that are in green, how many carbons are in them? There are 2 carbons in this bridge, and there are 2 carbons in the other bridge in green. The bridge that's in blue, how many carbons are in that bridge? Let's throw that out there to my students. It's not a trick question. Mr. Dion does not like the trick question.
Is it 2?
No, there's not 2. It's just 1 because this is just a methylene, right? It's just a CH2. So there's only 1 carbon in there. So the 3 numbers that go inside the square brackets are the numbers of the carbons in the bridges. You start with the biggest bridge and you go to the smallest bridge. Well, 2 of the bridges have the same number of carbons. So we put a 2, then you put a dot or a period. You put a 2 for the other bridge, and then you put 1 for the last one. So that's how you name this compound. So this compound, same compound, would be bicyclo-2,2,1 heptane. Okay, it's all based off of the bridge head carbons. Now, let's see here. What if you have a substituent on your bicyclic compound? If I was to have just this plain old compound, and forgive me, I'm going to try my best to draw it here. Mr. Dion ain't the best. He ain't the worst, but ain't the best at drawing these. Okay, so this is the bicyclic compound. Here are the bridge heads like this. The total number of carbons that we have in here is 1, 2, 3, 4, 5, 6, 7, 8. So this must be some kind of bicyclooctane, right? It's bicyclooctane. And if we look at the bridges, we have 1, 2, 3 carbons in this bridge. So we have a 3 here. We have 1, 2 carbons in this bridge. And then we only have 1 here. So it's 3,2,1, bicyclo-3,2,1 octane. But what happens when we have a substituent? So you see that here we have a methyl group over here. All you would do to name that compound is you would just put that it's an 8-methyl, right? Because you have an 8 here. But you might be wondering, why is it 8? Why didn't they give it the number 1? Because you start at a bridgehead carbon when you're numbering the parent, and you number the longest carbon chains first, or the longest bridges first. So we could start at either this bridgehead or this bridgehead. In this example, it won't make a difference. We're going to go through the longest bridgehead, the longest bridge. The longest one has 1, 2, 3 carbons in it. The second longest bridge, we keep following the chain. We go, has only 2 carbons in it. And then we go up to the smallest bridge. So since the smallest bridge is where the 8th carbon is, this would be 8-methyl bicyclo-3,2,1 octane. Okay? Now, if you look at the examples down here, it shows you the incorrect way of doing it. We have a methyl group right here. What would that be? Would it be a 6-methyl or a 7-methyl? The answer is it's a 6. It's not a 1. We start with the longest bridge. Okay, so we're going to start at a bridgehead carbon. We're going to go 1, 2, 3, 4, 5, 6, 7, and then up to 8. You have to keep numbering consecutively. You have to follow the order of numbers. 1, 2, 3. You can't go 1, 2, 8 or something like that. It doesn't work that way. If we had started numbering at this bridgehead, it might be a knee-jerk reaction for you to say, come on, Mr. Dion, why can't you just go 1, 2, and then give it a 2-methyl? No, because the first rule says you have to go through the longest bridge first. So you might be wondering, well, come on, this number 1 is closer to the methyl than, this number 1 is to this methyl. Yeah, but if you follow the order, it won't give you the lowest number for the methyl. Let me show you. You go 1, 2, 3, 4. We've gone through the longest bridge. 5, we wrap around 6, and then we end up with a 7 instead of a 6. Okay, so we have to always go through the longest bridge first, and we start at the bridgehead, which will give the first substituent the lowest possible number. All right, well, with that in mind, let's try naming a bicyclic compound. And if you're like, that doesn't look like anything you showed us before, Mr. Dion, before they all had like funky bridges and stuff. Well, we still have 2 cycles and they're stuck together, okay? So there are no carbons in the third bridge. Let me show you what I mean. If we start at the bridgeheads, we have a bridgehead here, and we have a bridgehead here. Should I start, if I color code them, could anybody tell me, should I start numbering at the one in red or the one in blue, following the rules that we looked at in the previous slide?
Blue.
I'm going to start at the one in blue. Exactly, because if I was to go, here's the longest bridge, right? I'm going to go this way. I'm going to go 1, 2, 3, 4, 5, right? Like that. If I go this way, then I've got 1, a substituent at carbon number 1. If I go the other way, if I start on the blue carbon, then I've got 1, 2, and then I have 2 substituents on here. So I'd have 2, 2, okay, instead of just a 2 here. And so that's going to be my tiebreaker. So we start on the carbon in blue. What's the first rule? We go through the longest bridge. So we have 1, 2, 3, 4, 5. What's the next longest bridge? We got 6, 7, 8, and there is no other bridge, right? There's nothing doing this or anything like that. So the last bridge has actually no carbons, right? And if you're like, I'm not sure, Mr. Dion, I know that this is some kind of bicyclo. I know this is some kind of bicyclo octane because I've got a total of 8 carbons. That's true. Okay, but let's look at the bridges. Here we have our bridgehead carbons. In this bridge, we have 1, 2, 3, 4 carbons. In this bridge, we have 2 carbons. So we've got a 4, then a 2, but there's no other bridge. There's nothing like this or anything like that. So the last bridge is actually a 0. So this is a bicyclo 420. Now we've got 4 substituents. They're all methyl groups. So we've got a methyl group here, 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 and here. So we have 2, 2, 5, 7 tetramethyl. So this is a 2, 2, 5, 7 tetramethyl bicyclo 420 octane. All right. If we have time, we'll come back to the bicyclic structures later, but there's a lot of content to cover in this chapter. So we're going to have to move on from there. And we're going to move on to section 4.3, which deals with constitutional isomers. Isomers are simply compounds that have the same molecular formula but have different structures. I think the classic example that I always bring up in class is C2H6O. Okay, it can either be this, which is, I'm drawing ethanol, or it could be this, which is dimethyl ether. And those are 2 very different compounds. Well, the same thing can exist for an alkane. If you look at these 2 compounds here, these are both are C6H14, right? They both have the same molecular formula. This compound is hexane, right? You memorized that this morning. This one, if we go 1, 2, 3, 4, 5, this would be 2-methyl pentane, right? So they are different compounds, different IUPAC names, different physical properties. Okay, very different compounds. Okay, different connectivity of atoms. So it's important that you understand the difference between isomers and constitutional isomers. So I'm going to back up a second just to address one question. A student asked me, can we only have 2 bridges? And the answer is no. Okay, when you're naming a bicyclic compound, you're always going to have 3 bridges. So if it's something like this, then the third bridge is just a 0. All right, so constitutional isomers. Well, this is a question that comes up on, so I teach nursing organic chemistry sometimes, so organic chemistry for, nursing students. And, sometimes they'll come up with questions like this on their standardized exams where they'll say, let's say you have C4H10. How many possible isomers are there? And you're like, well, let's see, there's butane, and then there's 2-methylpropane. So those are possibilities. What if you have, C5H12? Well, let's see, you've got pentane, you've got 2-methyl-butane, and then you've also got this right here. So this would be 2,2-dimethylpropane. So those are the possibilities. But you see that it gets out of hand really quickly. Once you get into more and more carbons, you get into, you get up to 15 carbons, there's 4,000 possibilities, and 40 carbons. I mean, then it's just, maybe I'll put that as a bonus question, right? Draw all the isomers of C40H82. Anyhow, it gets out of hand really quickly, and there's no simple formula for us to predict how many how many constitutional isomers there are for a specific formula. I have a question for you. It might seem like a silly question, but I want to see if you understand what's going on here. What if I had 100 carbons in a molecule? Could anybody tell me how many hydrogens you would have in that molecule? If it's a saturated alkane, like all of these, like if you were to keep going down to C100, how many hydrogens would you have?
202.
202, exactly. Because the general formula here for all of these is CnH2n plus 2 for all of these alkanes. All right, so if I have C100, I multiply 100 by 2, that's 200, add 2, 202. All right, so you've got to be able to recognize different structures as either being isomers or the same compound. Now here we have C6, right? We have C6H14. All of these compounds are C6H14, but we have a few different isomers. The ones that aren't highlighted, this one, this one, this one, and this one, those are all constitutional isomers of each other, and this is a constitutional isomer of it as well. But you need to be able to recognize the fact that these two compounds are identical. These are not constitutional isomers. How do you know that they are constitutional isomers? Well, you can do a couple of things. The first way is the easiest one, and that's probably the one you're going to master eventually, which is manipulating the molecule in 3 dimensions in your mind, right? All they're doing is taking the molecule in the first green box and they're rotating it this way a little bit, okay? And then they're rotating one of these bonds right here because there's free rotation around a sigma bond, right? Any single bond has free rotation around it. The other option, and this is I only use this rule when I've got no other option in my availability. And, you know, if you're really, really stuck, you're caught between a rock and a hard place, you can just name them. Okay, and you see that here you'd have 1, 2, 3, 4, 5. So this would be 3-methyl pentane. And here you have 1, 2, 3, 4, 5. And so this would be the exact same name. This is also 3-methyl pentane. Okay. If they have the same name, they're the same compound. Now, again, I don't like to use that rule a whole lot unless I really, really need to. Anyhow, I want to talk very quickly about section 4.4, and we're going to skip section 4.5 for the most part. But I want to talk about the relative stability of all these different isomers. Okay, so say, for example, we look at these 3 compounds here. We have 1, 2, 3, 4, 5, 6, 7, 8. So this is octane. So all of the compounds on here are some isomer of C8H18, right? Using the formula CnH2n plus 2. 2 times 8 is 16, plus 2 is 18. If you look at these 3 compounds, and I would like you to make sure that you read this section of the book. It doesn't take very long. But if you burn, if you cause all 3 of these hydrocarbons on here to undergo combustion, they all have the same molecular formula. What you find is that the heat of combustion or the enthalpy of the reaction is different for all 3 of them. And you're thinking, come on, you're getting the same products. You're getting 8 carbon dioxides and 9 water. You're adding 12.5 oxygens. It's the same balanced equation all 3 times, but you're getting different enthalpies. Well, the reason why is because the more branching you have, so here's the more branched one. You can see there's, you got 2 methyl groups here and 2 methyl groups here. The more branching you have on a compound, the more stable it becomes. So you see that this one gives off the least heat, so that means it's already the most stable to begin with. Now, the reason why is based off of something called proto-branching, which is way beyond the scope of our class. Don't worry about that word. I'm never going to ask you. If you have an inquiring mind, you're like, I can't fall asleep unless I know all about it, go ahead and research it, but it's way beyond the scope of our class. All you need to know is this down here. This is what you need to know for your quiz and for the rest of the class, is that branched alkanes are going to be lower in energy and more stable than straight chain alkanes. And this concept is going to come back in chapter 6. Now, the whole thing that I'm starring here, that might be worth the value of maybe 1 question on your next quiz. Okay, it's definitely not going to be a whole section on it. This past summer, I was teaching this class, and I had a student in the class who asked an interesting question. It's a question that I just assumed. You should never assume things, right? No, that's not good. Assume that your students understand everything. And the student said, what's the purpose of this reaction? You know, where are these alkanes coming from? And, you know, you think about molecules like methane, ethane. Methane is a major component of natural gas. If you think about propane, everybody knows what that's used for if you've ever used a propane barbecue. Butane is found in a butane lighter, right? Or maybe a butane-powered curling iron or something if you go camping. Anyhow, then you get into pentane, hexane, heptane, octane. Everybody's heard the word octane, right? You've heard about a high octane performance or some silly thing like that in maybe a music review. But octane, you see that when you go to the gas pump, it'll say, what's the octane rating of this gasoline? So you've heard that word before. And the student asked, he said, where do these alkanes come from, man? Like, where do you buy these alkanes? And I said, they all come from petroleum, right? They all come from crude oil. You know, if you turn on the news and it gets to the finance section, there's always something or usually something in there about crude oil, right? How much does a barrel of oil cost and how many are they processing from this well, you know, in Saudi Arabia or wherever. And so that's where all of these hydrocarbons come from. They all come from the petroleum industry, and they're all separated by distillation. Now, I'm probably not gonna ask you anything about this slide, but just so you know, you should have an idea what the hell we're talking about and where, things come from. So when they process a barrel of crude oil, only about 20% of that is gasoline, is the actual fraction that's found in gasoline. So we have other ways of, producing or a greater amount of gasoline out of a barrel of crude oil, and that's through cracking and refining. It goes over it in the textbook. I'm not going to ask you about cracking, and I'm not going to ask you about refining, but in case you're interested, you'd be able to learn more about the petroleum industry and where gasoline comes from. If you've ever seen Jeepers, Mr. Dion's got molecules on the brain. If you've ever seen the movie There Will Be Blood with Daniel Day-Lewis, right? They start, drilling for oil. And the main reason that people drilled for oil back in the 1800s was to get kerosene, because kerosene burned very cleanly, right? And, if you think about human history, people lived in the dark for a long time. The Dark Ages is a real thing. There's even paintings, of families sitting around a table with one candle and everybody trying to do things by one candle. And candles were expensive, obtaining the wax, and then people used whale oil, but there's obvious problems there. First of all, you're destroying the whales. And second of all, whale oil burned very, very sooty. It had a very sooty flame. So have you ever heard the expression, go outside and get some fresh air? That's where that originated, was from burning whale oil. Anyhow, I think it also originated from some of the first paints, but anyhow, it's kind of a history lesson. Has anybody here read the book At Home by Bill Bryson? At Home. This has nothing to do with chemistry directly. Has anybody read this book? Or A Brief History of Everything? No? Okay. Anyhow, if you want a really entertaining read, if you're like, I don't have enough work to do already, I would highly recommend this book. It's one of the coolest books I've ever read. It's all about the home, and anyhow, he talks about whale oil and stuff. Anyhow, yeah. So think about asphalt. It's on a road. When they tar a road in the summer, where does that come from? It comes from the petroleum industry as well. But asphalt has a really high boiling point, right? Asphalt doesn't disappear into the air. Anyhow, we'll stop talking about that. This is just a picture I threw in here. I took this off of Google Images or something, but this shows you how the distillation is done. You start with the crude oil, and then you have all the different fractions in there. Anyhow, I won't spend too much time on that. And let's get into what are called Newman projections, right? You can really shake your fist and say Newman, just like Jerry, right? Anyhow, Newman projections were developed by Melvin Newman at Ohio State University a long time ago, back in the 1900s. Anyhow, it says here, the rotation around carbon-carbon single bonds allows a compound to adopt a variety of possible 3D shapes called conformers. That's to represent the three-dimensional shape of a compound. And we have the wedge and the dash here. We have what's called a sawhorse, and we also have what's called a Newman projection. And we're going to focus largely today, or the rest of the lecture, on Newman projections. Let me show you what the hell a Newman projection is first, pardon my language, by going back to my camera here. Oop. All right, can you guys see? I have a model here. There's a light in the background. Come on. Here, there we go. There we go. That looks a little bit better. So this is a model. It's called a fever model.
I can't see anything. Sir,
It
you're still on
says
your screen.
branching.
Can you see my screen now, or you see my model?
No.
I see
I
your
can see your
screen.
screen, but not your camera.
That is weird. How about now? Can you see it now?
No, sir.
No.
You have to switch to your main camera, the one you use to focus on your face.
I have. It just isn't working for some reason.
There you are.
There. Is it working now?
Yep.
Yes, sir.
All right. This isn't my first rodeo. I've used the camera many times. Anyhow, so this is an ethane molecule. So this is CH3, CH3. Anyhow, so you can see here's my ethane molecule. And if you're wondering, hey, Mr. Dion, some of your hydrogens are black and some of them are silver. I know. Okay. Anyhow, these are called Feezer models. They're pretty expensive, but there's a lot of cool things that you can do with Feezer models that you can't do with the regular ball and stick models that you get in a general chemistry lab. Anyhow, the first thing is that we have free rotation around a single bond, right? This is a single bond. This is the carbon-carbon bond, and we have free rotation around that bond. So when you rotate, the bond, these are all different conformations. This is a conformation, this is a conformation, this is a conformation, this is a conformation, right? So there's literally an infinite number of different conformations that the molecule can exist in. If you look down the carbon-carbon axis and you spread all of the hydrogens as far away from each other as possible, that is called a staggered conformation, okay? Everything's as far away from each other as possible. The angle, let me hold it up here. The angle here between two hydrogens, whether it's these two or these two down here, the angle between those would be 360 degrees divided by 6. So that angle is 60 degrees, okay? We call that a dihedral angle. Again, this is called a staggered conformation. If I rotate that by 60 degrees, I get this where everything is blocking everything else out. We call that an eclipsed conformation, and the dihedral angle then between the hydrogens is 0, right? If I just turn it a little bit, you can see there's a little bit of an angle, but again, when it's fully eclipsed, I have 0 degrees. So eclipsed, there's a 0 degree dihedral angle, and when I turn it like this, 60 degrees, I get a staggered conformation, and the dihedral angle, or the angle between these two hydrogens, is 60 degrees, and all the repulsions are minimized in the staggered conformation. Now, as far as the wedge and dash goes, the wedge and dash would be looking at the molecule like this, kind of, okay? So you can see that this hydrogen is going out and back. This one is coming towards you. This one is in back. This one is coming out towards, this one's in the plane. This one's going in the back, and this one is coming out towards you. So that would be a representation of a wedge and dash. And a sawhorse is when you would turn it on an angle. It'd be kind of hard to show it like this. But anyhow, that's what a sawhorse would be. You kind of turn it on an angle. And you might be wondering, why do you have so many different ways of representing the same molecule? And the answer is, it depends on the situation. When you would apply which way of, or which technique of viewing the molecule, if you will. All right, so let's go back to my slides. So let's see here. Can you guys see my slides again? Section 4.6.
Yep.
All right, good. So
Yeah.
again, the Newman projections are really good for assessing relative stability of conformations resulting from the rotation around a single bond. So what I was doing is just spinning this bond here, right? And I was showing it to you like that. And again, this angle here is 60 degrees in the staggered conformation, and we call that a dihedral angle. So a Newman projection is the perspective on looking straight down a particular carbon-carbon bond. All right, so if we're looking down this carbon-carbon bond, if you see the viewer is looking down, you can see their eyelash on the top. So the carbon-carbon bond is this one here, going from this carbon to this carbon. What does the viewer see? The viewer sees this when they look down the bond. Why would that be? Okay, well, this carbon here that I'm put the blue on here, that is this one right here in the center. What's coming off of that carbon? I have a methyl group right here. This is a methyl group. But all of these, the methyl group, this carbon here, and the chlorine, everything I have in green here, kind of pointed out by the green line, those are all in the plane, right? In the plane of the viewer. And so everything that's in the plane is going to be vertical like this. What else is on that carbon that I have the blue dot on? Well, not only is there the methyl group and the rest of the molecule, but there's a hydrogen going in the back, right? And there's a hydrogen coming out in front like this. We don't draw those because this is a bond line structure, but they're there. If I label these HA and HB, if the viewer is looking down this axis, right? Could anybody tell me if I circle this one over here in black, would that be HA or HB? Anybody manipulating that in their mind?
HB.
No, it's not HB, it would be HA. The reason why is because the viewer is looking down here. Anything that's going in the back would be on the left-hand side, okay? Anything that's coming out in front, would be on the right-hand side, okay? So you see, since HA is in the back in this specific case, it's going to be on the left-hand side, so that's HA and that's HB. If we look at the methyl group, okay, the methyl group is going back, right? This methyl group is going back into the page. So if the viewer, again, is looking down this way, okay, the methyl group is going to be in the back like that. And so the viewer is, again, kind of looking down like this. So it's going to be on this side, the left-hand side. So there's my methyl. And then there's also a hydrogen here that's not drawn in, okay? We'll call that HC, and that would be this one here. Now, sometimes it's helpful to, do all manner of things. I'll see students like literally picking up pieces of paper and turning them on edge and things like that. If that's what you've got to do to rationalize it in your mind, do it. You do whatever you can to be able to draw a Newman projection properly. Now, something that I learned from my boss, Dr. Anderson, who's taught this class for probably 35 years or something, is something that he told me is that if anybody in the class has experienced building models or maybe working on a car engine where you're used to looking at pictures in 2 dimensions and then working with something that's in 3 dimensions and then going back and forth like that, he said often those students will master the idea of being able to manipulate things in their mind, and they can do it a little bit quicker. So what I want to do here is I want to draw what the observer sees when she or he looks down this carbon axis right here, this carbon-carbon bond. I'll highlight it in yellow. I'm not a mega fan of the way this is drawn for your first practice problem. I'm going to help you out with this one a little bit. We'll say that one of these chlorines is on a wedge, and we'll say that this chlorine is on a dash, okay? So this, one of them is coming out in the front and one of them is going in back. And if you're wondering, Mr. Dion, how would I know that? The reason you'd know that is because generally speaking, anything that's in the zigzag like that, that's going to be in the plane. Okay, that's in the plane of the observer. What else is in this molecule or on this molecule that's not drawn? Now we could kind of spruce it up here. We've got a methyl group here. We've got a methyl group here. But on this carbon, we have 2 hydrogens, right? That's CH2. We know that that carbon is tetrahedral. You have a bond here and a bond here that are in the plane. So that means that there is a hydrogen going in back and there is a hydrogen coming out in front. So something that I neglected to say on the last slide is that the second carbon, okay, the second carbon of the carbon-carbon bond you're looking down, that's the one that's represented by the circle. Okay, that's the second carbon. So let's start by drawing what we can see. We'll start with the first carbon. Maybe I'll color code them again. So we'll make a little dot like that. Then we have the carbon in the back, this one here. Okay. Now, what is in the plane? Okay, in the plane, up and down, in our vertical plane. Well, everything that's in the plane is everything that's not a dash or a wedge. So we have a methyl group going up, right? This methyl group is pointing up from the person's eye. That tells me that there's a methyl group sticking up like this. What else is attached to that carbon? I have a hydrogen going down into the left, and I have a hydrogen going down into the right. If I label them HA and HB, if I circle this one in red, could anybody tell me, is that HA or is it HB?
HB.
Yeah, it's HB because it's going in the back, right? That's pointing in the back. You got to twist the molecule in this direction, right? You're going to twist it this way and twist it back that way when you're viewing it in the Newman projection. So this, in fact, would be HB. This one would be HA. We have this methyl group in the plane, so that's going to be pointing down like this. Then we have the two chlorines. Now, since they're the same substituent, we don't really have to worry about it a whole lot. We've got one chlorine up here and one chlorine up here like this, but if I label them A and B, then it gets a little trickier. If I call this one A and I call this one B, if I circle this one in blue, could anybody tell me, would that be the chlorine labeled A or B?
A.
Exactly, because it's going behind the page, right? It's going in back. So this would be chlorine A and this would be chlorine B. All right, now if you're a little confused on all this, we're kind of running out of time, you're going to have to do some practice on this. There is nobody who gets out of, studying Newman projections without doing lots and lots of practice. I've already covered the concept of the dihedral angle with you when I switched over to my camera. Okay, I said that the dihedral angle is 60 degrees when everything is fully staggered like this. Another name for dihedral angle is torsional angle. And I also went over what is a staggered conformation and an eclipsed conformation. Now, when they draw an eclipsed conformation in a textbook, they can't cover the hydrogens up perfectly. But yeah, that's how we would draw an eclipsed conformation. Anyhow, all right. And you can probably guess that this is going to be higher in energy, right? Because these hydrogens are so close to each other, right? They're almost, they're going to be blocking each other. And so that's going to cause a strain. In fact, the difference in energy between these two conformations is 12 kilojoules per mole. So what I would like you to do before class on Friday, because you can see that it's kind of like, organic chemistry is a bit like the frog in boiling water, right? It gets a little more complicated as things move along. So what I would like you to do, and also today's lecture is very different from some of the other things that we looked at, right? Today, we're looking at drawings and manipulating drawings, whereas last class we talked about pKa's and acidity and looked at molecules and all that kind of stuff. So what I highly recommend that you do from now on, and I've told you this before, but I've taught the class enough to know that, reminding your students is not always a bad thing. So first of all, I would always read the textbook before coming to class. At a minimum, I would always try the problems that are in the slides before coming to class. And if you have time left over, try some of the problems from the text, because you have a whole solutions manual to guide you through that, okay? I will freely admit, I was an organic chemistry student for a long time. I studied it in graduate school, and I can honestly tell you that in a subject that I've dedicated my life to and I really thoroughly enjoy, for me, somebody who is very passionate about it, and I don't expect all my students to be passionate about organic chemistry. I'd be insane to think that. But in order for me to do well in school and to understand what was going on in lecture, I always had to read ahead of time, right? You got to have a little bit of knowledge about what I'm going to say before coming in, because there's just so much content and so many concepts that just hearing me teach it one time, the first time, I would think it's kind of difficult to learn it that way. But again, you can take my advice, and you don't have to take my advice if you don't want to. But something that I'll just kind of whet your appetite with for Friday to get you excited about Friday's lecture. This is a cyclohexane molecule, C6H12. It's not a benzene. Benzene has 3 double bonds in it. Anyhow, but this is a cyclohexane, and this is where we're going to get next class. So when you read the chapter, you're going to learn about the chair. Right? This kind of looks like a chair to you, doesn't it? Doesn't it look just like an Adirondack chair, right? You can put your back here, put your tuchus there, put your legs down here. Anyhow, next class, we're going to talk all about cyclohexane. Oops, I dropped it. And how, I know class is over, just give me 1 second. How cyclohexane can flip. It can do a ring flip. And I don't mean like a pancake, like flip like that. I mean it can rotate its bonds. Watch this. You see this? Methyl group is pointing up. Watch this. Poo-poo. And then you flip it. And now the methyl group is pointing out like this. So it's kind of cool. Anyhow, something to kind of get you excited about Friday's lecture. And yeah, there you have it.